Electric currents and its effects. Magnetic effect of electric current. Electricity does an interesting thing when it is passed through a coil. It makes the coil behave like a magnet. You know that a compass needle normally points in the north-south direction. It only gets disturbed when it is brought near another magnet. The compass gets disturbed here because the coil is behaving like a magnet. Let's see an activity. For this, you will need an empty matchbox, an electric wire, a compass needle, an electric cell, and a bar magnet. Take the cardboard tray from the matchbox. Wind an electric wire a few times around this tray. Put a small compass needle inside it. Now, connect the free ends of this wire to an electric cell through a switch. Now, note down the direction in which the compass needle is pointing. Bring a bar magnet near the compass needle. Watch the needle carefully and move the switch to the on position. What did you observe? Does the compass needle deflect? Now, move the switch back to the off position. Does the compass needle come back to its initial position? When the electricity stops flowing, the compass doesn't get disturbed. What does that tell you? That the coil stops behaving like a magnet when we don't pass electricity through it. Hans Christian Ørsted was the scientist who noticed it for the first time. It is such an important discovery. Because of that, we could start using electricity to make magnets which we could switch on and off. The magnets that we make this way are called electromagnets. Let's check out how an electromagnet works. Take around 70 centimeters long piece of insulated wire and an iron nail about 6 to 10 centimeters long. Wind the wire tightly around the nail in the form of a coil. Connect the free ends of the wire to the terminals of a cell through a switch. Place some pins on or near the end of the nail and switch on the current. What happens? Do the pins cling to the tip of the nail? Now, switch off the current. Are the pins still clinging to the end of the nail? The coil in this activity behaves like a magnet when electric current flows through it. Let's see how it happens. When the electric current is switched off, the coil generally loses its magnetism. Such coils are called electromagnets. An electromagnet is a magnet that is created using an electric current created by electricity. Since electricity can be turned on and off, so can an electromagnet. It can even be weakened or strengthened by decreasing or increasing the current. Electromagnets are used in all kinds of electric devices, including hard disk drives, speakers, motors, and generators, as well as in scrap yards to pick up heavy scrap metal. They are even used in MRI machines, which utilize magnets to take photos of your insides. Electric bells use electromagnets too. Let's see how. You know that the bell rings when you push the switch. It rings and stops and rings and stops, and this goes on as long as the switch is pressed. Let's see what's going on inside the bell. Inside, there is a coil of wire that acts as an electromagnet when it is switched on. There is a hammer near the coil. The handle of the hammer is made of magnetic material. When you press the switch, the circuit gets complete and the coil becomes a magnet. Then it attracts the handle of the hammer. The hammer moves towards the coil. Above the coil, there is the gong of the bell. When the hammer moves towards the coil, it hits the gong of the bell and makes the sound. But when it moves towards the coil, it breaks the circuit. When that happens, the electromagnet is no longer an electromagnet and stops attracting the handle of the hammer. Then the hammer goes back to its place. When the hammer goes back to its place, again the circuit is complete and the coil becomes an electromagnet. Then it attracts the hammer handle and the hammer hits the gong. Then the circuit breaks again and it goes back. This keeps on happening as long as the switch is pressed. That's how you keep getting the dings in the doorbell. Let's see how it happens.
An electric bell consists of an iron core on which is wound a wire as a coil. One end of the coil is connected to one terminal of a battery and the other end to a steel rod that acts like a spring for the hammer touching the screw contact. The other terminal of the battery is connected to the screw contact with a switch in the middle. Electric current flows through the coil when the switch is on, and the iron core acts as an electromagnet. The iron core attracts the hammer towards it. The hammer hits the bell and produces a sound. The circuit breaks at the screw contact when the hammer moves towards the iron core. At this point, the iron core ceases to be an electromagnet. The hammer is pulled back to its original position due to the spring action of the steel rod, and then touches the contact again to complete the circuit. The circuit is completed and current flows through the coil again, and the hammer strikes the bell again. The process repeats itself and you hear a ringing sound since the hammer keeps hitting the bell until the switch is released.
What did we just learn? When an electric current flows through a wire, it behaves like a magnet. A current-carrying coil of an insulated wire wrapped around a piece of iron is called an electromagnet. Electromagnets are used in many devices.